All right, I think we should get started. People are returning from the coffee break, so welcome back to the DSM conference Montreal. We are now moving to the second activity of today's program, which is actually a keynote speak from Heidi Jugovich, who is with us today. So first of all, thank you very much, Heidi, for being with us. We know you have a very busy agenda, and it's much appreciated that you take your time to come here, share your experience with us. So just before starting, I will present you, reading your CV here, the text that I have in front of me, and then I'll leave it the floor. So just for those who do not know Heidi or do not have the time to read her bio on 4 ways. So Heidi Jugovich has a 14-year experience on defense engineering with an emphasis on results-driven model-based systems engineering and enabling the digital transformation. She is an INCO certified systems engineering professional. She was the chair of the MBE Community of Practice for Northrop Grumman from 2016 to 18, and she's currently co-chair of the Digital Engineering Community and Practice of SAIC. Heidi is also an Army veteran who served as a missile defense early warning engineering operator and technician for 2 years, and finds motivation as an engineer by making a difference in the mission and in the day-to-day effectiveness and safety of a warfighter. So it's an impressive CV. Thank you very much for being with us once again. So your talk would be about how the SPS that you were an expert to could be working with DSMs. So thank you very much once again. I give you the floor.
All right, thank you so much. And thank you everybody for being here today. As was mentioned, I work for SAIC, and I was asked to actually come here and represent an industry perspective on how we as a company might use DSMs to solve problems in our day-to-day lives. And for those of you who don't know, SAIC is a big government, basically engineering company. We work with civilian and we work with defense and aerospace companies, primarily doing engineering work across the entire life cycle. And specifically, I work in a department that is responsible for what we call the digital transformation. And digital transformation means that we have stopped using, or we're trying to stop using, tools like documents and pictures to capture information about the systems that we are designing and building and testing and sustaining. And we are trying to use databases and models and more sophisticated analytical techniques. In particular today, I'm going to be talking about models, and specifically architecture models. This is just one piece of the digital transformation, but it's sort of the hub around which everything that we do in the digital transformation circles. Architecture is a key concept for systems engineering and for defense and civilian projects, the kind of projects that we do. They're very complex, and we use architecture to try to manage that complexity. And when I say an architecture model, I'm primarily talking about a model that's captured in systems modeling language in a tool like Cameo or Rhapsody. And these models capture information about the architecture that included structure, what are the pieces of the architecture, the interfaces between them, and the behavior. What functions does each component of the architecture have? How do those functions interact with each other, both inside of a specific component and between different components? And other properties of the architecture, such as size, weight, performance, those kinds of things as well. All of that is captured in these models. And primarily what we use models to do is to manage complexity, communicate better. We're really hoping that we can increase the quality and success of our programs, capture knowledge better, and try to train people better as well. And specifically during this talk, I'm going to emphasize that first one. Manage complexity. Because when we talk about why are we engaged in the digital transformation with DoD and aerospace in the civilian sector, the number one reason that people mention is that systems are becoming too complex to do it the old way, that we need models in order to manage that complexity. So while there are many reasons why we engage in the digital transformation, the focus that I'm going to be hitting today is to manage complexity. And so again, we're abandoning kind of those old methods, PowerPoint, Word, Visio, with kind of made up pictures and symbols to express what are the components of the architecture and how they interact with each other. And we're going to a formal language. And we're also abandoning flat files. I mean, Excel, You can kind of treat it as a database, but it's essentially still a flat file system, and you have no control over the individual elements in the way that you would as a database. So we are kind of throwing out these old methods that we do, and we're trying to focus on these new ones. And as part of that focus, we are really, really, really focused on how do you build a great model. All across DoD and industry, this is a preoccupation. How do I build a great model? And the main reason is because it's actually really easy to build a bad one. The languages are very broad, they're very complex. We have very few people who have been doing this for any significant, amount of time. And people tend to approach the building of the model as, let me take the information that was in my old document or my old PowerPoint and let me put it in this new tool and use it in the same way as I used it before. And that gets you a bad model. And so we're very, very focused on model craftsmanship. SAIC is no exception. We invested a lot of money and resources into our own digital engineering validation tool, which is our method, we think, of building a great model. But sometimes we are so focused on that, building the good model, we've got our nose so hard to that grindstone that we can't see what we're trying to do with the model. We just are focused on having the model. And you all should be pretty familiar with this problem of having something and actually using something. For example, we're heading into Christmas time. Maybe some of you are going to be, asking for some presents to help you for your, your New Year's resolutions in the future. Like, lose a few pounds. COVID's been rough, let me tell you. And so you might, get a treadmill. And I think many of you, if you've ever had a treadmill or some other piece of exercise equipment in your home, understand the basic principle that having the thing doesn't help you actually accomplish your goal if you don't use the thing. You actually have to run on the treadmill if you want to lose some weight. Having the treadmill isn't a magic item that you bring into your home and will suddenly cause you to start shedding pounds. And yet, in DoD and in our industry, we often think that having a model, a really good model, is suddenly going to cause us to, go faster and better and have good quality and achieve all those goals. But often we will try to build a good model without asking ourselves the fundamental questions of systems engineering, which is ironic because the model builders are usually systems engineers. The fundamental questions of systems engineering, which are who are the stakeholders and what is the use? And can the use of the stakeholders be accomplished by what we have put in the model? Just as we ask these questions for every system that we want to build, we need to ask these questions for the models that we want to build. If we don't consider how we want to use the model, it doesn't matter how beautifully we craft it, it is almost certain that we will not be able to accomplish the use because we didn't consider it when we were trying to decide what content to put into that model. So if I'm telling you that one of the reasons why we're building models in the first place, is that I want to manage complexity, what does my model need to do in order to give me that use?
Appears we have lost Heidi for a moment.
Yes, I think the connection broke down.
Hello?
Okay, she's back.
Oh, I don't know what happened there. I could hear all of you. You can hear me now, though?
Yes.
Yeah. Okay, great. Okay, yeah. So how do we actually try to use these models, that we build? We focus on the proper use of the language the model is built in, which is SysML. And SysML is a graphical language. You build diagrams. And we love SysML because it's a graphical language, because these diagrams really communicate really well. One of the first triumphs that I ever had, I guess, using model-based systems engineering was when we were trying to clarify some confusing requirements, and the engineers thought it meant one way, and we kept explaining the words to the end users in the field. I'm talking about like enlisted soldiers, in the field, explaining what the use of this was going to be. And the soldiers kept nodding their head and saying, yeah, that's what we mean. We put the diagram on the screen, and with very little training on how to interpret the diagram, because these diagrams are pretty intuitive about how they read. They said, nope, that is not what we meant. And so that graphical language ends up being this great communication medium, between the engineer and people who are not as technical to understand how we are intending to make the system behave. And just putting our engineering concepts into a formal language, into SysML, means that we're no longer like creating symbology on the fly in Visio or on PowerPoint and then putting a key on there and then using the symbology, incorrectly, that we've just invented on our PowerPoints. We get some rigor just by using a formal language instead of illustrations anymore. And the model is in the background as we are creating all these diagrams, creating this wonderful, rich relational database. It is full of dependencies. And for those of you who are far better experts at DSM than I am, the dependencies are a really important thing that you would like to analyze about your architecture. But we don't do that. The diagrams are a trap. We are so in love with the diagrams that basically that's the only way that most people are trying to consume the models that they are building, is by looking at all of the pictures. If your model is simple and for a simple system, you can do this. But remember, the reason that we have built the model, again, the use of that model is to manage complexity. And if you have a complex system, you are likely to have a model with millions of elements in it and hundreds of diagrams. And so if my method of managing complexity is to put all of this information into a series of diagrams, then my method of consuming this information is by looking at the hundreds of diagrams. Have I actually managed any complexity at all? Have I accomplished my use case? And I would argue that no, I haven't. So my use case for DSM focuses around this idea of how can I understand and analyze my model for architectural goodness in a way that isn't just a bunch of experts in a room flashing past the diagrams and going, oh yeah, that looks good. That seems like a good idea. We have concepts of what is architectural goodness. And recently I worked with a colleague and he had something like 50 different criteria, 50 different things that you could optimize for, in an architecture. The ones that we hear about the most often are cohesion, coupling, cycles, things that I'm sure, again, from DSM, many of you are familiar with. And also, we want to optimize our architecture for something that we call MOSA. And MOSA is specific to the defense industry. It's a requirement basically that architectures be modular, that they be, cohesive and not coupled, the components are, and that the interfaces between them are really well defined. But unfortunately, that requirement is on almost every DoD program, and it's more or less just rubber stamped, and people don't do anything with it. And so we don't treat it as a real requirement, and as such, our architectures really suffer. So what I'm suggesting, and the thing that we at SAIC have been experimenting with, is that DSM can be a way that we could take the information that we have built in this model, and we built it using the diagrams, but there's data in the background. We can use that as a tool to analyze those dependencies in ways that might be meaningful for us to optimize architectures. So, in a model, we have many different types of dependencies. Some of them are like the functional dependencies. We define functions and we assign them to different components in the model. And so, for example, in the top little picture that you can see over here, if mission control doesn't send the location data to the ranger, the ranger can't determine its physical state. This is from an example model that we built. And that's a dependency, that would show up in your DSM. In another diagram here that you really can't read because it's super complicated, we also define the interfaces explicitly, in the model. So the functional dependencies tend to be kind of implied between the components, and then we define formal interfaces between those components. Those are also dependencies, that are there. So we have the functional dependencies, we have the interfaces that are implied by behavior, and then we have the formally defined interfaces, and all of those are things that we would like to be able to analyze more robustly than we currently do. So the modeling tools already have the ability to display something that looks vaguely like, a DSM. They're called matrices, in the model. Every modeling tool out there that's a mature modeling tool has this capability in here. And you can display almost any kind of dependency that you want in here. That leverages the dependencies that are inherent to SysML. But also you have to understand, when I say developer specific underlying meta model, people establish their own patterns in the model of how they define an interface. Like, for example, those interfaces that I defined, the two functional interfaces on the diagram, that was using operations and an object flow between the two of them. There are other methods that you could use, like call operations, and control flows. So you have to understand specifically, in order to analyze these dependencies, how the developer has used the modeling tool and how they have used the language. And so you can show all of this if you understand those things, if you understand how SysML works and you understand how the person built the model, you can show all of these things in matrices in the existing tools, but it's really the presence or the absence of the dependency. It shows you kind of what's already there. There really isn't a capability inside of the model to say whether that dependency is good or bad, whether it's violating some sort of an architectural rule that's there. And there's really currently no way to apply an algorithm to this to suggest how those dependencies might be refactored. Could I move some functions from one component to another and get a better architecture? We do have some capability to do this using automated validation in some of the tools. Rhapsody and Cameo both have the capability to define rules and say, if I've got two operations that are talking to each other in two different components, I need an interface that allows that. So there's a certain amount of internal consistency analysis that you can do, but these aren't really like algorithms that are making any kind of suggestions, and it still relies on somebody, manually defining the rules, which are very powerful, but it's not quite as far as we want to go in terms of analysis. So what if we go beyond the architecture model and we pull that architecture model in to a DSM type of a tool? And I'm not talking about looking at the model and then hand entering it into a spreadsheet or something like that. I'm talking about automatically ingesting the model content, that rich database of millions of elements and millions of dependencies, and pulling them into a DSM in the same way that we often today pull in code. And this is an example that you're seeing on the screen here is code, software code dependencies that are there. But what if, the models themselves actually can be interpreted in a similar way to software code? What if I could do the same thing with model data that's there? Then suddenly I could look at my modeled architecture before I've built anything, before I've gone down the road of investing and developing components that I'm not sure I've defined in the most optimal way. And I can analyze that architecture using metrics. I can, use partitioning algorithms to help me determine whether or not, what are the qualities of my architecture. There might even be an opportunity here, and I'm not sure what these metrics exactly should look like. We're still struggling, with that. Maybe quantifying some element of model goodness. So that is kind of where I want to be. But beyond that, I've defined an architecture that I think is good. Did we actually go and build the product according to that architecture? That's the other problem that we have. Again, we're dealing with complex systems, millions and millions of lines of code, sometimes system of systems, type architecture that's here, and manual code review against a PowerPoint diagram to determine whether or not the coders actually built the architecture that we all agreed was going to be the architecture. It's not particularly practical. So how do we compare that complex architecture that's captured in a model, it's not in a picture, anymore, and that complex code implementation? And one of the questions that we have and that we're really interested in is that, can DSM tools be used to do this comparison automatically? Can we somehow align our definition of what we meant by dependency in the architecture to dependency in the code, and see whether or not they are consistent, whether or not the components that we have defined actually exist there? And not just do they exist, but are they interacting in the ways that we said that they should interact with in the architecture? and not, calling some element of the architecture that they're not allowed to call. Because what we often have is like the snowman picture here, we have this idea of this is the thing they're going to go build, and that's not what we get. And then not only did we not initially get what we thought we were going to get, it gets worse over time. The architecture degrades because on these big complex programs, people move on and off of these programs all of the time. And the architecture tends to go somewhere in a drawer, or the model, gathers dust somewhere. Nobody's using it to do anything. We've already built the thing. And the architecture loses cohesion because we lose that social understanding of what the architecture was. And we really have no way to efficiently enforce it. And so my dream state, and here I am as representative of the industry, is to be able to understand my architecture well up front, to be able to compare the as-built architecture to the intended architecture, and to monitor over time. And I think that DSM is one of the tools that can let us do that. So my overall premise here is that having a model for SAIC, having a model is only a first step in this architecture journey that we want. Sure, it's better than having no architecture or just having a bunch of pictures that we say are architecture. But just graphically interpreting those architectures using diagrams and models is still a really primitive state. That we want to get to the state where I can have a semi-automated analysis of the data that's behind my modeled architecture. And I think we need a variety of techniques, and that DSM is one of those techniques that's really promising here. And it's the one that we've been experimenting with the most. And then I want to be able to use those same sophisticated tools and analysis methods to carry forth that analysis into the implementation, and the implementation over time, so that I have the best architecture that I can have, and I can make sure that that is what my customer is getting in the field. So in conclusion, I'd like to say that basically where industry is making a mistake is that we're focusing too much on definition over analysis. And that we can build beautiful models, but unless we use them in sophisticated ways, use that automated analysis or semi-automated analysis that we've said is the reason why we're building, the model, that we're not really getting all of the juice out of the squeeze that we're doing here by building these models, which are complex and difficult to build in and of themselves. And so I would argue that we need better architecture analysis methods and tools, not just a better model, and that we need ways to check for compliance and to check for that compliance over time. And I believe that DSM is the tool that one of the tools that I would like to use. And so I believe I'm a couple minutes early, but I think we can go ahead and start questions and answers. Thank you.
Thank you very much, Heidi. Yeah, no problem. So we have more time for discussion.